I entered this field with the sort of the inverse problem that Mike was alluding to at the very end in the previous talk. The C-chondrites, among other things, among current falls, they're the most abundant, they're the most numerous, and as I'll show in a moment, they have a somewhat broad but discernible range of degrees of aqueous alteration phenomena. C-chondrites are abundant as the large clasts in some of the objects that Mike was talking about. And the community has been working on and off for several decades, trying to answer questions like these. And they're sort of solar system history questions. Were asteroids or comets the carriers of early solar system water, particularly to Earth? In what form was the water? OH groups and minerals or ice? There exists a variety of evidence of ephemeral or metastable liquid water. There are minerals that are pretty clearly alteration products. So what was that water like? And part of the challenge for people like me is what it was the water like if you don't have any, right? Mike has samples of the water. I don't. I just have the products, the alteration products. What was the water like? Liquid or ice, warm or cold, fresh or salty, acid or alkaline. What were the sources and pathways, the fate and transport of solutes in these ephemeral waters? I've worked in an environmental science department with a lot of hydrologists, and the way to get them to show up at my talks is to talk about fate and transport of solutes. Let's see, is this? Well, in this context, at this meeting, ocean worlds show evidence of water in different forms, rocky silicate cores, water-rock interaction. This is all we've been hearing about for the past day, and we'll hear more. What is that water like? And they're basically all the same questions. So even though I haven't worked on my chondrites specifically from the point of view of the ocean worlds problem, the questions are very similar, and the matter of understanding what the water might have been like or must have been like to produce the observed features in C-chondrites has been what I've been working on and off for some decades. Oops, that goes that way. Now, why study meteorites? Well, if you have the meteorites that Mike has, it's because they still have the water in them as these fluid inclusions. Other than that, there are many, many meteorites that don't have that kind of water in them. And the meteorites are pretty much the only samples we have of these objects, the only intentionally returned samples, the comet dust samples Mike just mentioned, and less than a thimbleful of grains from ordinary chondrite type asteroid, are the only samples the community has that are returned from a known specific object. So part of why we study meteorites is because we have them. We have samples, and as the Natural History Museum of London has on the sign outside, we investigate meteorites to understand how the solar system works. So with that, the background, I justify the title of my talk, and the subtitle, Serpentines and Their Composition Tell Us Some or Something About What Was in the Water on the Parent Bodies of the CM carbonaceous chondrites when the aqueous alteration took place. And of course, I forgot this. I'm building this around a review of these 4 papers that Mike Zielinski and Eric Tanui and I published over the past several years. And for work backwards, previous work, you can refer to those. And I'm going to integrate some more recent work that other groups have done with this work as well. I love this diagram. It's the one diagram that we've seen before that I'll show again. Water, rock, pictures of rock. I like pictures of rock. Enceladus, I'm very happy after the first talk that it's the one that I picked because it's the only one where my subject matter might be directly relevant. Elsewhere in the meteoritics community, there are models, visual representations of what rubble pile like parent bodies might be like if they had ice in between or ice coatings on the grains that could be encapsulated at least for a while by a solid crust and become liquid water to participate in these reactions. There was a great slide a couple talks back where a rocky core of Enceladus might look something like this. My comments in the title about microporous, I really wasn't going to talk specifically about the porosity very much, but I do want to point out right here at the beginning, that any system like this, whether it's a small static system, a somewhat larger convective system, an exhalative system where the water gets out in a single pass through the rock, is, among other things, a dual porosity system. There's porosity of various kinds within the rock, between the grains. The CM and CI carbonaceous chondrites have bulk porosities in the low tens of %. And then there's the macroporosity in between the chunks of the rubble. So in that sense, we're dealing with the smaller scale porosity and associated reactions. Mike talked about a variety of carbonaceous chondrites, stony meteorites, stones, chondrites, carbonaceous chondrites. CMs are the most numerous, the most abundant. There are hundreds of them, many, many dozens of witnessed falls, and they exhibit a fair amount of variety in their alteration features. A quick review of the cast of characters. The common minerals in all chondritic meteorites include the two I'm going to talk about the most, olivine and serpentine-group minerals. Others exist and react and contribute things, and I'll talk about that in a moment. In the background is a picture, of a backscatter electron microscope image of a carbonaceous chondrite and a pseudomorph. For the non-mineralogists in the room, pseudomorph means false form. It's a mineralogical term several hundred years old for the situation in which there's a mineral now that exists in the shape of a different mineral. Evidently, the serpentine replaced the lovely, well-formed crystal of olivine here. So the formula, olivine formula serpentine, is not unfamiliar to this group. Many reactions can be written to describe, many stoichiometric expressions, mass action expressions can be written to describe what's going on here. Here's a hypothetical olivine with some water, a serpentine, magnetite, including the oxidized iron that makes this possible. This is a reaction from the planetary literature, but it is based very much on terrestrial serpentinization, in which the serpentine group minerals really are way up at the magnesium-rich, near the magnesium-rich end member, partly because there's another sink, another product that can incorporate the oxidized iron more easily. We'll see in a moment that in the CM2s, it's really not like that. Specific minerals serpentine group minerals that'll come up in the presentation in a few minutes include most workers who want to give a specific mineral name to a magnesium-bearing serpentine in a carbonaceous chondrite will refer to it as chrysotile. Chondritic is a really important player. It has 3+ iron in both octahedral and tetrahedral sites. And then greenolite is a mineral that includes a fair amount of iron, much of which, I would argue in our situation, all of which is divalent. One of the introductory remarks yesterday was about talking across communities and across language, and even within a community there are sort of dialects, there are graphical dialects of these ternary diagrams. There are at least 3 different ways of plotting these. Weight percent of the oxides of iron and magnesium, and those are the octahedral cations for the non-mineralogist in the room. Those are tetrahedra, silica and aluminum and trivalent iron occupy those. These are the apical, the corners oxygens of octahedral sites in the serpentine group. The usually octahedral cations are shown on one limb. The usually tetrahedral cations are shown on the other. And typically, we'll see in a moment, the materials that are being microprobed here, the matrix materials of diverse chondritic meteorites, when they're microprobed, the grains themselves are often smaller than the spot size of the microprobe. So a lot of the probe analyses are averages. The excitation volume of the instrument excites signal from a mixture of materials. And so there's a lot of scatter in many of these. And we can see there are iron-rich ones. There are other minerals we'll talk about in just a minute. There's a range of Chondritic, here they're calling it antigerite. Another dialect of this diagram is to make it weight percent of the elements. Yet another dialect of this diagram is to make it atom percent of the elements, mole percent of the elements. And then yet another dialect is to rotate these diagrams in different ways so the iron isn't always at the top corner. Sorry that several different dialects will come up in a moment here. Remarks have been made, John Rummel in particular made remarks about going into certain situations with certain expectations. And so here are some quotes from a paper. I don't want to pick fights, so I won't cite the paper and name the authors, but these are direct quotes about what is expected, what is assumed in going into some of these studies. There's a sentence to the effect that the starting composition of the anhydrous component, in this case the olivine, controls the composition of the thioylosilicate formed by reaction of water. All right, and there's the reaction that they publish, a generalized formula for olivine with a generalized formula for serpentine. That's in the introduction. In the discussion, without saying anything about it in the methods or results, they basically say in the case they're looking at, the chondral olivines are forstaritic, and therefore one will form a magnesium-rich serpentine, and that's in the discussion. And then they conclude the olivine. They include from the composition of the serpentine what the olivine must have been. But that assumes these things here. Those are the expectations they went in with and the assumptions they went in with. We'll come back to that in a bit. So here's a backscattered electron microscope image of a chondrite. A colleague of mine came into the microprobe one day when there was an image like this on my laptop for my what am I looking for, a context image. He said, "Is that a carbonaceous chondrite?" I said, "Yes." He said, "Those are the ugliest rocks in the solar system." Beauty is in the eye of the beholder, I guess. The main textural constituents in carbonaceous chondrites are chondrules, little round silicate sleet, frozen once molten silicate droplets, fine-grained rims around the chondrules, isolated grains of coarse-grained minerals of things like olivine and pyroxene that aren't parts of chondrules, and everything in between is matrix. I spent a little bit of time looking at matrix, but my work has been a kind of a needle in a haystack look at other aspects of the problem. The chondrules contain olivines in particular. And the first group to publish work on this, Adrian Brearley and one of his PhD students, looked at chondrules, looked at the iron-rich olivine in particular in the chondrules, and came up with a kind of a scale of not altered, slightly altered, extensively altered, and almost completely replaced in all cases by serpentine-group minerals. Now, after decades of work, their four-part system, Eric and Mike and I expanded this way to even more altered examples, and other workers have presented work that expands it back towards less altered materials than the original range that Hanowski and Brearley covered. The first ones we'll talk about is the most recent work by Pignatelli and others, which requires us to, on a specific CM chondrite, which requires us to introduce one more mineral to the cast of characters. And that is this layered magnesium, iron, nickel hydroxide sulfide mineral called tochilinite, which can occur as a discrete mineral, or it can occur in a regular one-to-one interstratification with a serpentine group mineral. The older literature referred to these tochilinite-bearing materials as poorly characterized phases. Ian McKinnon and Mike Zelensky figured out what they were some years ago. And here is a TEM image of one of these 18 angstrom superlattices of a regular alternation one-to-one of tochilinite serpentine. These tochilinite serpentine cronstedite, member of the serpentine group, tochilinite cronstedite intergrowths are pseudomorphic, false form, after olivine and pyroxene in a few local places in the Paris CM chondrite, which other than these local situations, little clasts or little isolated grains outside of clasts, other than that, Paris is the least altered meteorite known. And the alteration products in these pseudomorphs, after olivine in this case and pyroxene in this case, include iron-bearing materials that include these tochilinitic materials. Following a suggestion that I made to them based on work I had published about 3 or 4 years ago, I recommended to them they try an isovolumetric reaction. In the case of the replacement, and only in that case, I'm going to make the argument that a volume of olivine is replaced by an equal volume of serpentine. There are no expansion fractures. The serpentine isn't bigger than the olivine. There's no textural indication that the volume now occupied by the serpentine is somehow different from the volume occupied by the olivine. I want to say really clearly, I have no dog in the fight on the matter of whether that applies in any other setting, but I think there's textual evidence for that in this setting here. Using that isovolumetric reaction, basically 5 olivines go to 2 serpentines, Pignatelli and others probed some of the olivines they had, and I'll say in a moment, I think that's a little bit of a problem because there's no olivine left in any of these pseudomorphs. They don't know for sure what the olivine was that was the precursor of any individual one of these pseudomorphs. The olivine is all gone. But they used what they knew, and oh boy, it came.
15 minutes. 15 minutes.
Oh, 15 in, thanks. All right, that I might be able to do. Okay, thank you. And wrote a reaction that, among other things, because they started with such a magnesium-rich olivine, you can't form cronstedite of the observed composition unless you import iron as a mobile solute into that volume of the pseudomorph. There wasn't enough iron in the olivine, the precursor, to enable populating all of the crystallographic sites here. All of it was divalent to begin with, some of it is trivalent now, and we get the redox phenomenon that gives rise to the hydrogen of interest. That's in the least altered known of the C-chondrites, and iron was imported into the pseudomorph. The work that we published, and you can read most of it on the more altered meteorites on Nagoya and Queen Alexandra range, we have partial pseudomorphs after ferroan olivine and after near-end member magnesian olivine. We can toggle back and forth between the outlines of the crystals here, and we can see classic meshwork serpentinization textures in the magnesian olivines and a more center-seeking replacement starting at the periphery in the case of the more iron-rich olivine. And furthermore, some of the iron-rich olivine remnants and the pseudomorphs around them clearly show decorations of iron sulfides that you don't see in the same meteorite, in the same class, basically, around the serpentines replacing the magnesium olivine. If we were to draw, so here are the probe analyses. This is an atom percent with the tetrahedral cations on the top and the magnesium iron solid solution across the slide. Using some careful selectivity, some certain filters of criteria for quality of analyses, unlike those clouds of data in the previous ternary diagram, we find data that plot right along the 40% atomic proportions line that corresponds to the 40% octahedral sites, 40% tetrahedral sites, 60% octahedral sites in the structure of serpentine. So these are good stoichiometric serpentine analyses. And they're pseudomorphs after a whole range of olivine compositions. We have the remnants of the olivine in the center of the pseudomorphs. And in Nagoya, all olivines alter to serpentine of exactly the same composition. Same thing, although not as broad a range of olivines were microprobed this way for the Queen Alexandra range meteorite. So the argument that the composition of the reactant controls the composition of the product is wrong. The composition of the product, serpentines, is within a very narrow range, almost identical, regardless of the composition of the olivine. Now, science self-corrects. One might argue that the view of a direct inheritance of composition is a mistake. And that the uniformity of composition, at least in these settings, was something not that's expected. And I always like this quote from Journey to the Center of the Earth, because in the good translations, it reveals that the protagonist, uncle, is a mineralogist, which I gotta love. Science is made up of mistakes, but they are mistakes which is useful to make because they lead little by little to the truth. Well, as just one example, doing the same kinds of calculations for the whole range of olivine compositions observed in the cores of these partial pseudomorphs. The most iron-rich olivine has so much iron in it, that iron can be exported because there's more than enough iron needed to form the observed composition of serpentine. Down at the bottom, basically pure forsterite, there's no iron in it. It requires import, as Pignatelli suggested, and there's a hypothetical intermediate composition at which there's just the right amount that iron would be conserved. Any olivine more iron-rich than this will form the same serpentine but export iron. Any more iron-poor than this will form the same serpentine but have to import iron. So here's my diagram that was published in 2015. What elements leave the olivine in what proportions, which ones are incorporated into the serpentine, whatever isn't incorporated into the serpentine according to those reactions can move outward. The decorations of sulfide around the edges of one of the iron-bearing ones, iron-rich ones, indicates that iron interacts with extra dissolved sulfide in the solution to form the sulfide mineral decorations around the edges. And I want to point out that there's no redox involved at this advanced stage. All right. So I think what I'll do is leave it with these observations and inferences. The olivines are diverse. The serpentines have more or less homogeneous compositions. Some of what we went into with expectations was right. The iron-bearing ones do alter faster than the iron-poor ones, but some was wrong. The olivine composition doesn't control the serpentine-magnesium-iron ratio. An isovolumetric reaction, different reaction in a different paper is inconsistent with modal abundance observation, so some other reactions that have been used widely before can be disqualified. And at this stage of the reaction, the iron was a mobile solute with an external and not apparent mineral control of product composition. The last conclusion slide. Iron substitution in serpentine group minerals after anhydrosilicates varies, and it was controlled by the solution. The redox state varies among the different meteorites in the in the field of silicates. The least altered ones have the most oxidized iron. The most altered ones are the most reduced. And there are interactions of the iron with the sulfide. And all of this is mediated by the fluid medium that is in between all of these little clasts and grains and chondrules and so forth, with species having to diffuse through the surrounding matrix in order to get from one place to the other. Thank you.
At risk of getting between you guys and coffee, let's have one quick question and then we'll hold the rest for the discussion maybe.
Are the serpentines porous?
Porous? It turns out they are. I've used higher resolution microscopy since, and at least some occurrences are. I was just probing those last week. I'll let you know at the next meeting what that means.
No.
Yeah, my attempt at the short answer will be that these coarse-grained constituents make up at most a few tens of % of the total volume, and that most of what's happening in these rocks is controlled by whether there are or are not volume changes and things like that in the matrix.